Good morning, everybody. Oh, thank you for the rousing response there. So we're going to start off with most of you, if not all of you, should be familiar with this type of figure that I'm showing here. So this is the reservoir storage. The height of the column is acre feet. And then in red, we see the loss in terms of reservoir sedimentation. And these are ranked. So from left to right is most filled to least filled. So what this figure illustrates is the question that I want to address today is, where does all that sediment actually come from? So John showed this slide yesterday, and we're focusing on the sort of green parts, the reducing the upstream watershed sediment yields. And this diagram sort of illustrates why it's important to figure out where that sediment is coming from, because I don't think landslide stabilization is going to work particularly well in Kansas. Okay, so there have been lots of studies all throughout the Midwest that have shown that stream banks contribute pretty significant amounts of total watershed sediment yield. Specifically for Kansas, Kyle Yurchek and Andy Ziegler, formerly of the USGS, did a sediment fingerprinting study for Perry Lake and showed that channel bank sources were the dominant source for that reservoir. And this sort of makes intuitive sense when you start looking at Kansas streams. So I'll put some pictures there on the right. This is pretty common. And seeing as Colin is our guest, it's always good to get one of your classic figures in there. So we're looking at that scenario at the top there, which are these rotational failures. So lots of examples there on the right. The bottom right image, the white arrow, points to that kind of rotational failure surface. You can see all the slump box, these beautiful kind of arcuate head walls. So this is pretty common, kind of like mass wasting, stream bank erosional process in Kansas streams. So you just look at it and you see, of course, that's the dominant sediment source, right? And so because of that, a lot of effort has gone into stream bank stabilization. So the Water Office has this awesome interactive map, and it shows you the locations of these kind of stabilization sites. So all the blue dots on there are constructed sites. Green ones are planned. I think the yellow ones are kind of currently under construction. So you can see where they have been primarily focused. So it's on the Big Blue and Little Blue rivers upstream of Tuttle. It's on the Delaware River upstream of Perry, and then in the Osho and Cottonwood rivers upstream of John Redmond. And if you're not familiar with stream bank stabilization projects, there's an example there of typically what they look like. So you've got your failing bank on the left, and then you're going to grade that down. Usually it's like a 3-to-1 ratio. Put in some toe protection, maybe some rock veins, plant some native grasses, maybe some riparian vegetation. But one of the main goals of all that is to stop those kind of like rotational failures from happening. So we can ask this question, do these stabilization efforts work? And the answer is really a question of scale. So we're going to take a bit of a sidetrack and sort of look at this, and then we'll loop back around to the main question that we're trying to look at. So let's look at the local scale first, or site-specific scale. So we did a lot of post-construction monitoring, drone surveys for 14 sites on the Cottonwood River. And it's just a kind of good example of how you can do these drone surveys, create the DEMs, do the subtraction, create these DEMs of difference. So the image there in the middle shows the red is erosion. So this is what happened after, I think it was like a week after construction when a flood event came through. So you can see that red band there, that's erosion just along the kind of like toe protection. The image on the right, this bank is, I think, like 4 or 5 years after construction. Again, if you look at the lower right, you can see that kind of band of red there. But that red blob up there, kind of close to the top right-hand corner, that is actually one of those rotational slumps that's happened in between two of the rock veins. So these projects do continue to erode, but certainly not at the same rate that they were previously. So here's a sort of summary figure that we put together. The orange bars are pre-construction volumes of material eroded. This is per year. These are normalized for different bank lengths, normalized for variable discharge between the periods we analyzed. The whiskers on those represent kind of like range of variability between the different time periods we looked at. But the blue is from the post-construction drone surveys. So the take-home point there is a notable difference in terms of the amount of material being eroded. And if you take the averages, it's about, depending on where you look, 62 to 94% decrease in sediment yield. We can also look at kind of just the drone surveys, and you can compare, so the yellow dots are stabilization sites, and then you can look at unmodified sites along the same reach, so those would be the kind of green dots or squares. Bottom right is the unmodified sites, bottom left is the stabilized sites. You can see there's a clear difference. If you kind of take some averages, you get 68 to 78% decrease. So this local site-specific scale, absolutely, these stabilization sites do a great job reducing sediment yields. What about if we think about the reach scale? So thanks to Tricia and Carrie and Corbin from K-State, Corbin did this HEC-RAS modeling for his master's degree. So these are two sites on the Cottonwood, C112 on the left, C102 on the right. The white bracket there on the left is where the stabilized portion of the bank was. And you can see that kind of like yellow color there. So this is showing the difference in stream power between before and after construction. So that yellow band there is an increase in stream power, and that just happens to be right where you typically see the kind of erosion immediately above the bank toe protection. More concerning, however, is if you look downstream where that red arrow is pointing, that is the downstream meander bend, whereas there is a notable increase in stream power. And then a similar thing for the image on the right at C102. So the stabilized portion, it was a big one in between the two white lines there. Again, you can see that yellow band all the way around, just above the toe protection, and then a significant increase in stream power as you look at that downstream meander bend. We also did drone surveys of those downstream bends. So that's what these plots here. Each one of those periods represents roughly a year, except for period 1 where we went back and used the 2010 LiDAR and then did the DM of difference between that and our first drone survey in 2019. So the green bars there are pre-construction, and the yellow bars are post-construction. So you notice immediately after construction, there is this large increase in erosion on those downstream meander bends. But after like 1 to 2 years, it actually tails off and gets back to kind of what you saw pre-construction. So it seems that this is a kind of like temporary effect downstream, and that the channel is able to kind of adjust to those new conditions. Now, admittedly, this is an N of 2, so we only looked at these 2 sites, but John and I are looking at a couple more, and we're going to see if this is actually kind of a similar phenomenon that we see at other sites. And there's probably a big difference as to where that next meander bend is, right? So lots of things still looking into. So at the reach scale, there are some questions immediately downstream as to how effective these are. But let's talk about the watershed scale. So when we ask that question, do stabilization efforts work, what we're really asking is, do they reduce the downstream sediment yields to reservoirs? And that is a pretty tough nut to crack. So I've got a quote here from the Army Corps from their Kansas River Reservoirs Flood and Sediment Study. So that quote is, the number of stream bank stabilization sites completed, which at this point is more than 250, with past and current levels of funding, which has been millions of dollars, have not remediated reservoir sedimentation issues. So it has been suggested that an order of magnitude more stabilization sites would need to be constructed, so we're talking about hundreds per year instead of dozens, would need to be done in order to potentially notice an effect. Another way of looking at it, though, is, well, what if we would focus our efforts to where they were most effective? So that loops us back around to this question of, well, where exactly does the sediment come from? So one of the ways we can tackle this is to do sediment fingerprinting. So simply, it's just a modeling tool where you can unmix a composite sediment sample into its constituent source fractions. So what that means is our composite sediment sample is going to be our reservoir sediment. And then the source fractions, the ones we look at, are stream banks, cropland, and grassland. So here there's an example from the Cottonwood and Neosho watersheds upstream of John Redmond. We went and actually took some lake cores for there, and then the brown dots where we took our source samples for stream banks, the yellow dots are the source samples for cropland, and the green dots are the source samples for grassland. So if you look at the plot on the upper left there, so the white dots would be our composite sediment samples, so that would be our lake bed reservoir sediment. And then you can see the different, I probably should color-coded those differently. So let's say source 1, red, that could be stream bank. Source 2, let's just imagine that's yellow, that's going to be cropland. And then the green one is going to be grassland. So that plot shows two particular traces. When you look at those two traces, those reservoir samples plot slightly closer to the stream bank source, right, to the red box. And we look at like 50 different traces. This just shows two. So you can imagine doing this multiple times, right, and getting these different relationships. And then you use the Bayesian modeling to kind of pull that all apart and to like apportion those results. So for that particular example there, you can imagine those reservoir sediment samples, let's say 70% stream bank, if you look at that plot on the bottom left, 70% stream bank, let's say 20% cropland and 10% grassland. So that's in general how it works. So we did this initially for John Redmond, and then we're now doing it for a total of 17 of the Kansas reservoirs. We've got 12 completed so far that I'll show results for, all funded, thankfully, by the Water Office. So Caden is doing all this work for his master's degree. So we have 50 traces, but actually we end up with 48 in the model because we combine some of the organics. So we use a radioactive isotope. That's plutonium. I'll talk about that in a second. The organics, we use like carbon, nitrogen, as well as their stable isotopes. And then to get the actual tracer, we would multiply, so in that particular example, it would be carbon multiplied by the stable carbon isotope of carbon, delta C13, to actually get the tracer value. And what this plot shows for those 12 reservoirs and then the 48 traces along the top, we only want to use the most informative traces in the model. So there are a variety of statistical tests that we can do to kind of narrow things down. So we use a range test, Russell-Wallace test, and then discriminative function analysis, and that narrows things down. And the traces that pop out as the most informative in general would be plutonium. So those are the ones with kind of like in the dark green color. Plutonium, that's organic tracer where we multiply carbon by the isotope value, and then beryllium, uranium is another one that pops up pretty frequently. So those are the traces we're using and how we narrow things down. So here's an example for plutonium as to how this works. So we've got our stream bank sources, our cropland sources in the middle, and our grassland sources there on the right. So in the 1960s, I don't know that I would want to get close enough to take a picture like that, but bomb testing in the 1960s actually created global atmospheric fallout all across the Earth of radioactive isotopes like plutonium. So that falls upon the landscape. Now, where you have a stable land surface, like grassland, for example, the plutonium activity is relatively high. So that's indicated there in the green box. Cropland, you get the same rain out initially of those plutonium activity, but then that gets worked in through agricultural practices, right? So it's less than a stable kind of grassland surface. And then stream banks, they should have zero because the sediment there is typically older than 1960. So you portion that out, that shows the plot there in terms of plutonium activity. And in this particular example, your lake samples, you can see where that plots in terms of plutonium activity, kind of in between stream banks there and cropland. So we do that for all of the informative traces after the statistical tests, and then do the apportionment. So this is what the results look like. So the first thing to note, so these are cumulative bar graphs, right? So stream bank contributions on the bottom, cropland in the middle, grassland at the top. First thing to note is they are not all the same. So the stream bank contributions in particular do vary. So Fall River is the highest, and that's about 69%, followed by Toronto, and then Perry. So those are the reservoirs that have the most dominant kind of stream bank fractions. On the other end of things, Tuttle has the lowest. So because there are these clear differences, the implication of that is we should probably focus on kind of tailor-made management solutions for each of these watersheds. There's no one-size-fits-all kind of scenario here. But the rest of the talk, I just want to focus on these three. So Perry, Redmond, and Tuttle. It was good, by the way, that Perry, we did find that it was dominantly stream banks, because that's also what Kyle and Andy found. So it's always good. They use different traces and slightly different methods, but so it's good that the kind of results are pretty similar. So let's look at why we might potentially have these differences. We're going to jump in and focus on John Redmond to begin with, because for Redmond, we did something like a little bit extra. So in addition to collecting our lakebed samples, we also collected samples from floods. So we went out, you saw some of the sampling equipment yesterday if you came to the field talk. So there's Caden there sampling with that Van Dorn to get suspended sediment during a flood event. And then we also set out those sediment traps. We can analyze, that's going to be our composite mixtures. So we can analyze all three and then kind of see what's going on with the sediment as it is transported through the fluvial system and then ends up in the reservoir. So things get a little bit more complicated. So on the left there that's the lake bed, so that's what's in the reservoir. So there's that low bank percentage, but it's dominated by cropland sources. But if you go to the other end and you look at what is actually we collected from the sediment traps, that actually is dominantly from stream banks. Okay, so there's a question. Why do we see these differences? And that brings up this question of the magnitude and the frequency of flood events. Okay, so high magnitude flood events transport disproportionately large amounts of sediment. Ariel with the USGS did a study for the Cottonwood and Neosho rivers using turbidity. So it was looking at the total suspended sediment load. And particularly I want to focus on what's transported by these out-of-bank flood events. So at the Plymouth gauge, which is upstream on the Cottonwood River, west of Emporia, 48% of the total suspended sediment load was transported during these out-of-bank flood events. But by the time you get down to the Neosho Rapids gauge, it's up to 78%. Okay, so the take-home point is there that most of the sediment that is transported, that ends up in the reservoir, happens during these out-of-bank flood events. Now, when you make one of these stage frequency plots, you'll notice there that all of our discrete storm samples and all of our trap samples were below that out-of-bank. We didn't actually sample one of those out-of-bank storm events. Okay, so what we actually did sample were those kind of more minor flood events that remained within the channel. So if they remain within the channel, guess what the dominant bank source is? It's going to be the bank material that's there that's able to be eroded and transported. And there's going to be minor contributions of cropland and grassland from runoff type processes. But that red arrow that I pointed there, so that's the very small amount of time where you get these big out-of-bank flood events. So that little portion of that stage frequency plot is what transports the vast majority of sediment. And this is what it looks like. So this is a drone picture here of the Neosho River in flood, so the confluence with the Cottonwood is highlighted right there. The blue arrow shows where the kind of flow would normally go. And here we see flooding. So wait a minute, didn't Colin say that flooding is a good thing? Not in this type of scenario, and here's why. So if you look at the bottom left, you can see like just downstream of the confluence, there's this big meander bend, right, on the Neosho. So what happens when it gets out of bank is you actually get these chute channels form which short circuit and bypass that meander. Now, that whole meander has a particular slope to it, right? But if you cut directly across it, you've got a much steeper slope. So in those areas, this flood is not depositing sediment, which is what we would like. It is actually eroding sediment, and specifically it's eroding cropland sediment. So that cropland sediment then gets washed into the river system, transported downstream, and that is what ends up in the reservoir. So it's that kind of magnitude frequency consideration of flood events that explains why we get these differences in our different source fractions, specifically for why we got our kind of higher bank fractions in those traps, because we didn't sample these out-of-bank flood events. And this helps explain why, when we look at the lake bed mixtures down in Redmond, why it's dominated by cropland, because most of the sediment gets transported during these scenarios. So we can sort of take that idea and that principle and start thinking about the other reservoirs. So if we just look at the nearest upstream gauges, and we consider the out-of-bank flows, so these would be defined by the Weather Service, the minor flood stage. We're going to do more detailed analysis. This was a very quick one, just looking at the kind of like number of days that you get these out-of-bank flows. So on the Delaware, for Perry, at that particular gauge, it hardly ever floods. So if most of your floods are in the channel, that's a similar scenario to what we were sampling with our sediment traps. So that explains why the bank fraction for Perry is dominant. For Redmond, so on the Neosho, the average is 3.3, so it's those like pretty infrequent, but those large magnitude events that transport all that cropland stuff. And then look at Tuttle, so the nearest upstream gauge on the big blue, much, much greater. So maybe that would explain why we have such low bank fractions for Tuttle. is because of the magnitude and duration of these outer bank flood events. So we'll bring this home just by kind of thinking about watershed management solutions. So the two main ones that have been done kind of upstream of our reservoirs are obviously the stream bank stabilization, as well as kind of cropland BMPs. But I want to point out, I deliberately missed out part of the quote from the Army Corps. So it's not just the number of stream bank stabilization sites, it's also the acres of agricultural land that have had conservation practices implemented, as well as the number of stream banks that have not remediated the reservoir sedimentation issues. So that sort of points to, okay, maybe some more strategic implementation. So perhaps stream bank stabilization should be focused maybe on the Delaware River, where we know that kind of dominant sources do actually come from stream banks as opposed to Total. In contrast, maybe Total would benefit more from those kind of like cropland BMPs. And I believe Alexi is going to talk about cropland BMPs later on today. But ultimately, the kind of upstream reductions are just, a part of the puzzle. Really, the kind of in-lake management and restoring that sediment continuity is probably going to get us the biggest bang for our buck. So that's all I have for today. Thank you very much for your attention. I believe I've got time for a few questions. Sorry, for everyone else, the question was, when is hydrosuction likely to start on John Redmond? And the answer is, the plan was 27, but it's likely to be later than that because of permitting. Yes? So the question for everyone else was sort of along the lines of like stabilization techniques. To my knowledge, what I presented is pretty much the most common way of doing things. So the rock veins there are kind of designed to like divert the flow and such. But from what I've seen, I'm not too familiar with alternative designs that have been implemented. Sounds great, thanks. Scott.
So, what about streams that are not regulated by reservoirs? How do we do that? Because right now, what we've got is very, very tangible. Letting effects. Those reservoirs are up and down, they let, they go, they let, they go. You have flooding in between the reservoir letouts. How do you thought about those type of scenarios?
Yeah, it's a good question.
The Neosho River, for example, is very heavily managed.
Sure, that's because it has Marion upstream, but I mean, for most, like Perry, for example, I mean, I wouldn't say upstream of Perry is regulated per se, downstream for sure. And that's where most of the kind of like stabilization projects and the kind of, most of the samples we collected are from what I would say would be unregulated kind of portions of the watershed. So, doesn't really address your question, but. Right. So that's a great point by Scott, and if I didn't know better, I was thinking he's trying to plug something here. So for Soldier Creek, we're actually doing a sediment fingerprinting study, and the great thing about Soldier Creek is it has all of these kind of like soil health, upland BMP practices, and we're hoping to be able to kind of tease that apart as to what the effects are. So watch this space for more details to come. Yes, sir.
Sir, if I understand your presentation, you talked about two methods of measuring the erosion. You talked about the Layzell, you talked about the soil fingerprint. I presume that the Layzell is limited to measure changes in the elevation, is that correct?
Correct.
And so for smaller reservoirs, is there one technique that is more accurate or provides more resolution of where the erosion is coming from?
Yeah, so depending on the data sets you use, the resolution varies. So the statewide LiDAR, so back from 2010, I believe was probably like 2 feet resolution. But our drone surveys, so the LiDAR unit we have on our drone surveys is like centimeter scale resolution. So now it's limited to kind of like smaller reaches. You're not going to get the kind of broad spatial coverage, but for doing those kind of like stream bank monitoring upstream, downstream, like that's well within, so kind of centimeter scale resolution. That addresses your question. Yep. That would be a question I could not answer, but maybe somebody else in the room could. Colin. That's a great comment from Colin. In case people didn't hear, we want to keep the topsoil where it is right now. Yeah. Yeah. Oh, great question. So 25 years. Yep. Sure, good question. Yeah, haven't looked at that yet, but that's something, like when we actually do properly like the kind of stage frequency, we'll look into that, yeah. Okay. Chris, you're speaking next, so made this an easy question.
Yeah, I'm just trying to see myself. No, I was asking, has there been any monitoring specifically in the about the sourcing for cheap sediment
I'm not sure I fully understand the question.
Yeah, so specifically looking at, sediment trapping that's occurring in
Oh, I see. Yeah, not currently, but that is going to happen for downstream of John Redmond. So in preparation for potential hydrosuction, we need to get the baseline data sets So analyzing the amount of fines downstream, and particularly in riffles because of endangered mussel species, is on the list to do. So, all right, thank you, everybody.
All right, next we have Chris Jansen. Chris Jansen is the Freshwater Program Manager